Okay, so it's a pleasure to reintroduce Barak. Somehow, when I was first struggling to learn homogeneous dynamics, this was while working with Barak and babysitting his kids.
Thank you. Okay, so let me remind you, thanks for coming back, first of all. Let me remind you what the purpose of this lecture is. So in the previous lecture, I told you about some new results, and I want to tell you some of the ideas of proofs of these new results. So the two results that, to remind you, the two results that I want to talk about are the following. So we will give ideas behind the proof of the following two statements. So the first one, in the stratum H11, there is X such that the orbit closure of X under the Horocycle flow has Hausdorff dimension in, and now let me be slightly more precise, it's some number between 5.5 and 6, strictly less than 6, where notation U is the unipotent group in SL2R given by one parameter upper triangular matrices with eigenvalues 1. So we want to construct fractal orbit closure. This is this creature that I called the spiky fish last time. And another statement that I want to discuss is in H11 there are points not generic for any measure and this is just a fancy way. I said it in this way in order to make a contrast with Marina's results, which were particularly the genericity result or the equidistribution result that Enon mentioned as the third statement in his lecture. But in order to provide points which are not generic for any measure, in fact, what all you have to do is construct one point in one function for which the Birkhoff averages fluctuate. So in fact, what we're proving is we find a point and we find a function, a compact continuously supported function f, such that the limit as t goes to infinity, 1 over t integral from 0 to t, f of usx ds. In other words, the Birkhoff integral of the function along this particular trajectory does not exist. This limit doesn't exist. This object has fluctuations. This would a generic point has to obey a statistics given by some measure, and we're going to find a point for which we have these fluctuations. Okay, so those are the two results. Let me be a little bit more precise about the first result before turning to ideas. I'll draw a little schematic picture of the structure of the result. So there's a world, and I'll also remind you of some definitions. So we're in some big space H11, which is space of real dimension 9. Just to remind you, this is surfaces in genus 2, which have two cone points of cone angle 4 pi. And inside this space, there's some submanifold, which we denoted by curly E or E4. This is surfaces which can be exhibited as two tori glued along a slit, and the two tori are identical. Identical tori glued along a slit. So this is an object of dimension 5. On this manifold of dimension 5, there's some kind of fractally set which I will write just as a bunch of points. So this set, all these points, is a set called omega. Omega is surfaces in E which are minimal and not uniquely ergodic for the horizontal straight line flow. Okay, so I remind you that on a translation surface we have a notion of a motion along straight lines, and motion along, this has nothing to do with the Horocycle flow. And I showed you at the end of the previous lecture that there do exist surfaces for which this straight line flow is minimal but is not uniquely ergodic, and it's a fact that many of these examples actually already exist in this locus E, and in fact there are plenty of them, which is a result which I quoted last time. The dimension of omega was determined by Chung and Maser and I forget the and Hubert. Thank you, and it's 4.5. Okay, so this is a subset. Yes, Uri?
Why 4.5?
No, this is a kind of a deep thing. It follow. There's been a lot of work before getting this exact 4.5. It's really a lot of work, and sticking. What we're going to show is that sticking out of this set omega, there are these lines which I called the spikes, and our orbit closure will be there will be a point whose orbit closure will contain all of omega and also all of these spikes poking out to some fixed distance. Okay, and the spikes vary. So these are spikes are one-dimensional in a two-dimensional plane field orthogonal to this set E. Yeah.
That omega is dense. And
Yeah.
you're saying that the orbit closure contains all of omega. And
Right.
what-
Where's the contradiction so far?
If the orbit closure is closed and it contains omega, then it contains closure.
Right. The orbit closure contains E. Its dimension is bigger than E. Its dimension is 5. It's somewhere bigger than 5.5. So the orbit closure contains all of this thing.
So are we supposed to understand why is it fractal? It seems
Well, this is supposed to tell you that it's a fractal. It's between 5.5 and 6, not including 6. And I also showed you a picture of a fish. I don't know if that helps. I can't say more. So, okay, but in terms of dimensions, the dimension count is, this is a 5-dimensional object. On this 5-dimensional object, there's a 4.5-dimensional object. From this 4.5-dimensional object, you get one-dimensional things sticking out. They're not sticking out in a continuous way. They're sticking out in some kind of a measurable way. And we're able to control the Hausdorff dimension up to this extent. We don't know the Hausdorff dimension. Yes?
I guess we would like to have an example where you have a fractal not containing any submatrix.
This is a very good question. That I don't know if that's what Uri wants, but maybe that's what you want. Our constructions involve, you'll see better in a few minutes, our sort of constructions involve, we use the fact that we sort of understand the Horocycle dynamics on E very, very well, in fact. And so our orbit, our strange orbit, actually tracks a nice orbit. And we don't know how to produce somehow a strange orbit which does not track any other particularly nice orbit, okay, in some way, for the purpose of this result. For the purpose of this result, you'll find, I'll give you an orbit which has strange behavior, maybe. Okay, so this is the picture, and I want to gradually justify how we get to this situation. And in order to start, let me mention an idea which was very important in Marina Ratner's work, and this is the idea of centralizers. So let's do a little recap, or this is related to both Elon's talk and Manfred's talk. So this is this. Let's talk a little bit about this idea of slow divergence of nearby trajectories. And so, suppose you have this. Now let's do a little discussion in homogeneous dynamics. So, for x being G mod gamma and US a one-parameter flow. Yeah, let's take it unipotent. Let's define Z to be the centralizing group. So this is the elements of G which commute with all elements of U. And let's look at two trajectories. So we have x1 and we have x1 in x. x2 is zx1 in x. We have 2 points, and they differ by applying the centralizer. Well, then what happens, of course, is that if you just write down this equation, which uses the commutation of z and us, what do you see? Well, here is the trajectory of x2, here is the trajectory of x1, and to get from one to the other, you have to move by a fixed element. So what this means is that, in some sense, the distance between us x1 and us x2 is constant. They don't diverge, they don't come any nearer or any closer in time as a function of s. Okay, now in today's lecture there will be many uses of this expression distance, and this really doesn't completely make sense if you don't specify what the actual metric is. And so you should always just understand that when I say distance, I mean it in a certain vague sense. But you see so the picture you should have in mind here is x1, here is x2. There's a map taking us from x1 to x2, which is application of this z. And the map is continuously defined everywhere on the space. And at every point along this trajectory, it's the same map, which takes us from one point to the other. So in that sense, these two orbits are just parallel and tracking each other. On the other hand, so that's trivial. I guess I'll erase this now. On the other hand, the thing that Marina used in a crucial way is that if Z does not belong to the centralizer, or G, let's say, does not belong to the centralizer, and x2 is G times x1. And again, let's not be too pedantic. There are some technicalities about G should be small, perhaps, or something like that. You can look at this function. Let's draw. Then the function S maps to distance of US x1, US x2. This function behaves like a polynomial, and let me be a little bit precise about what I mean by behaves like a polynomial. It's not really a polynomial. In some computations, it's exactly a polynomial for some fixed degree. In other situations, it's like a rational function. But what Marina cares about is the following phenomenon. When you graph this function, first of all, in this situation, it's not a constant function, and it has some growth. And the growth is sufficiently slow so that the following thing happens. There exists an epsilon such that for all x1, x2, and all t, let's say this is the interval from 0 to t, if distance from ut x1 to ut x2 is 1, then the amount of time at which the distance is at least a half, say, is bigger than epsilon. Okay? So no matter where you start and how long you have to wait until these two trajectories move away from each other, they do stay away from each other in some window of some fixed proportion of size, and this is crucial to many of the arguments that Marina uses. What we want to do, or what we're going to do, and this is sort of the main point of our construction, is to show that in this non-homogeneous setting that we're dealing with, you can have something which sort of looks like a centralizer in some senses, but it violates this, and we're going to call it an erratic centralizer, and I want to explain. Let me call this an erratic centralizer and then give a state of proposition. So in translation surface dynamics, we can have something that you might call erratic centralizers. And what do I mean by that? I can find there is a map, a one-parameter family of maps Everything I'm doing today is just in this very special case that we've been discussing about H11 and omega, but this is a part of a much more general phenomenon. You shouldn't have the impression that this is just so restricted. But we have maps. The maps are defined only on this set omega. They come with a parameter t. You should think of this parameter t as being like the size of this centralizing element. So it's a centralizer, but it's not defined everywhere. It's only defined on omega. And it has the following properties, such that for every t, every x in omega, let me say some things. So first of all, if you apply the centralizing map to x and then apply the Horocycle flow, it's the same as doing this in reverse order. So this is really a centralizer. Notice that omega, the set, this is kind of an important point that I forgot to make. Omega is defined in terms of straight line flow in the horizontal direction. If you apply the Horocycle flow to a surface, you're shearing in the horizontal direction. You're not really changing the straight line flow in the horizontal direction. And so omega is invariant under the Horocycle flow. Okay? So this just means ZT centralizes the U action, at least formally. On the other hand, so for every t non-zero, let's say small, x is, so ZTX is not in this set E, and x is closest element from E to ZTX. So in other words, the centralizer is moving you away from E in an economical way. So you're moving away from E in such a way that the point you end up in, the closest element of E belonging to it, is actually x, the point where you started. Now let's look at the displacement or the distance from ZTX to x as a function of s. And so for all t non-zero, the distance, there exists a c, so that and all s, the distance from USX to US ZTX is positive. So you always stay away from the point, which means by the first item that you always, in fact, stay away from the set E, but you stay bounded as a function of S. And this is also for every x in omega. So this is the orbit, and this is the centralized orbit. And the centralized orbit is somehow tracking the original orbit, and it's not going too far away, so the distance is staying bounded. And finally, something that doesn't at all look like this. On average, the distance goes to 0.
In the update of how uniform is C, what is the order of those?
It says it's as it's written, for every t there exists a c, such that for all s, for all x. And for every t, for every x, the following is true: 1 over t integral from 0 to t, distance from usx to us ztx ds tends to 0 as t tends to infinity. So the average distance goes to 0. Let's draw the graph. So here is s, and this is the distance usx usctx between these two orbits. So this is this parameter c. So by the first item here, the distance is trapped between these two lines, and in fact it's some positive function, and in fact it's 0 on average without being 0. So it sort of looks like this. Maybe it goes down, and then maybe it stays bounded for a while, and then it goes up, and then something like that. So in order to, and I should have mentioned one last thing, and it doesn't go to 0. Dist usx usdtx does not go to 0, because s goes to infinity. So along a subsequence, you get it pokes away from 0 to some definite amount, but on average it's 0.
What is omega again?
Omega is the set of non-uniquely ergodic, minimal non-uniquely ergodic surfaces for the horizontal foliation and each one in E. Yeah.
Omega is invariant under U, and ZT centralizes. Why do we need the US in the third?
Why do I need what?
US.
Here?
Yeah.
Yeah, you could say this holds for every x in omega without the US. That's true. I just wanted to write it in this form so that it would sort of match with this picture.
What's the role of P?
E is, what's the definition or what's the role?
The role, because P here is not.
E is an important set for the discussion. It's a nice SL2R invariant set, which has a nice SL2R invariant measure, but for the properties of the centralizer, it's not really important.
For the P, so the parameter P, so you could take CP.
T, somehow you have these spikes, which I showed in the pictures. These spikes are what you get when you apply T. As you move along T, you get, I should have maybe said these centralizing maps are not continuous in the argument omega, but they are continuous in argument T. As you apply T, you just move away further and further. Any more questions about what I'm saying? So this is like the feature which one gets in these translation surface dynamics, which does not happen at all in homogeneous dynamics.
In the first condition, you need US X belongs to omega, because it's not.
So I said omega is US invariant. So if X is in omega, then so is US X. Okay? Okay, so what I want to do in this lecture is to explain how one gets this kind of weird centralization behavior and how one uses it to prove the two results that I said before. Okay, so the first goal is to, and this is the reason that this kind of behavior exists is exactly tied up with this phenomenon of minimal non-uniquely ergodic straight line flows on translation surfaces, which came up in my previous lecture. So let's talk about how does one get these non-trivial centralizers. And so why do erratic centralizers exist? And to understand that, we need to understand how the Horocycle flow is acting. So let's first talk about centralizers of the Horocycle flow. So examples of centralizers. For the Horocycle flow. Let's just do something that has nothing to do with translation surfaces, just the action of unipotent matrices on the plane. And this is a silly formula, but it's going to be crucial all the time. So this is how the Horocycle flow acts on vectors on the plane. So it takes a vector like this and maps it to a vector like that. So it tilts things. In particular, it does not affect the x-axis at all. In particular, if you take a vector and you add a horizontal vector to it, those two operations commute. So USV plus E1, say, or TE1 is USV plus TE1. E1 is the first basis of the standard vector, of the standard basis. So these are two operations which commute in the plane. You can translate horizontally, or you can apply the Horocycle flow. Okay, that's obvious. Now let's see how. Now I'm going to use Manfred's tricks. Now let's see how to use this when thinking about translation surfaces. So I've drawn for you a picture of a translation surface in blue. Let's ignore the red for the moment. And so the blue line with obvious edge identifications is a surface of genus 2. And the Horocycle flow, as I told you yesterday, is just applying these matrices to these polygons. And so this first picture is obtained from the other picture by, I don't know, some kind of small tilt in the horizontal direction. That's what's happening to these blue lines. They're shearing in this way. And what are the red lines? When defining the red lines, I'm defining a deformation of the blue surface, which only involves moving this vector by tilting it to the right, or in other words, I'm moving this blue point to this red point by translating it horizontally. And then, without affecting the rest of the picture, except what I have to. So this is just this is an example in pictures. I'm not telling you what's going on topologically or anything like that, but it's a local operation that I can do. I take the picture and I just move one point to the right. When I move this point to the right, this edge and this edge change, and I have to make corresponding adjustments on the bottom in order to make it possible to make a gluing. Okay? So this operation is just defined by adding something. If you want to be pedantic, and it's important for the rest of the talk, you can think about this in the language of cohomology classes. So what have I done to my cohomology classes? You can think of these blue edges as being a basis for the homology of the surface. And what's determining the geometry of a translation surface is the value that these get under homology, under an element of cohomology, I'm sorry. And I'm taking this element of the basis, and I'm adding a particular element of cohomology that adds this distance to this element of the basis and doesn't do anything to the other elements of the basis. So it's some kind of element of a dual basis, dual to this particular basis, written here in blue, if you like. Okay? Now, I do this operation here, I do the same operation here, and I can do these two operations in two different orders, and this commutes. The reason it commutes is because of this formula. In other words, I can first remove the blue line and replace it by the red line, and then apply the Horocycle flow. I'll get this figure, or I can do things in the opposite order. First apply the Horocycle flow, and then make the change up here. The change is the same change in the sense that it's the same cohomology class representing the change. I'm adding the same amount when I'm moving this point. Okay? That's how one constructs centralizers in general for the Horocycle flow. Yeah?
I'm not sure if what I'm asking makes sense, but from what you're saying, there is another, on the space there is another action, not just a simple action, but an action of the cohomology.
There's a local structure of this. The space has a local model, which is the cohomology space, and you can talk about translations, but it wouldn't be correct to call that an action. You have these, it's locally modeled on the cohomology space. You can make little loops in cohomology, so you can add things in some orders and get to 0 if it was a group action, but it wouldn't be acting as the identity on the structures.
Is it correct to say that it commutes with a certain vector field?
So there's a whole bunch of vector fields which commute with the Horocycle flow. Every vector field that only changes cohomology classes by adding horizontal vectors to them commutes with the Horocycle flow. Okay? But these vector fields, if they're defined in terms of cohomology, it's very hard for them to be well defined without making reference to a picture, or in other words, without making, yesterday I was talking about triangulations. If you don't make reference to a triangulation, it's hard to give a well-defined vector field that's defined on the entire space. And our goal now is to define such a operation in a way which makes sense without reference to a particular picture. Okay? And here's how it's going to be done. The operation that I now describe is going to be called the tremor map. So what is a tremor map? It's a certain kind of mapping of this form, but slightly more complicated, which has the property that it only moves things in horizontal directions and commutes with the Horocycle flow, but it's sophisticated in the sense that it does not depend on the choice of a picture. So what is a tremor map? Choose I'm going to write it out in full, and then there are going to be some terms which might be confusing. So choose a measure, a signed measure, nu on a surface x of total mass 0, and let nu bar be the corresponding transverse measure. Define ZT x in period coordinates by holonomy of ZTX equals the holonomy of x plus integration of nu bar applied to alpha, let's say. Okay, this is a formula. What is this about? So recall, let's write it over here. Recall that we had a certain cohomology class associated with any translation surface, which I denoted by hol of x. What is hol of x? Hol of x is an element of the cohomology group. It acts on a path on the surface joining points of sigma by integrating the two one forms obtained from the plane along the path. Okay? So this was the way that translation surfaces were given coordinates. These are called period coordinates. Okay? Now, let's do a little computation which will show us how the Horocycle flow acts on these coordinates. So I'm going to get there in a second. Yeah, I'm going to give an example. So dy exactly will be an example of a transverse measure. So let's talk about the holonomy of USX applied to alpha. In other words, when I integrate alpha, suppose I know how to integrate alpha with respect to x, what happens when I want to integrate alpha with respect to the new translation surface structure US of x? Well, the answer is integral dx plus s times integral of y, integral of 1. Okay, just a second, this formula should remind you of this formula. All I'm doing is I'm adding another term to the x direction, and the term that I'm adding to the x direction is what used to be on the y coordinate. Okay, but in terms of cohomology classes, what I'm actually doing is I'm leaving one of the cohomology classes unchanged, and to the other cohomology class I'm adding something, a multiple of dy. What's so special about dy? It's a transverse measure, so that's what I now want to explain. Yeah, sorry.
Alpha is a path
Alpha is a path.
in X, in the surface. So when you are integrating on the surface USX, you integrate US alpha.
No, so there's a model surface somewhere, S. On it there's a path alpha that connects two of these singular points, and there's a way of connecting these model surfaces with our translation surfaces by triangulations. So I can think about the same path as living on all sorts of different surfaces. It lives on the model path, and it has different geometries on these different surfaces, and this is how you get the geometries. The cohomology class tells you what the geometry is. Okay, now what's a transverse measure? So whenever you have a measure on a surface which is invariant under horizontal translations, it looks like this. So here's a patch. This is a little patch in a surface. Okay? And on this patch, I want to describe to you a measure that's invariant under horizontal translations. So there's a measure disintegration, which says the following. You can take any vertical arc. You can put a measure on this vertical arc. Let's call that nu. And you can put length measure on horizontal arcs. Let's call that dx. And then the measure will locally have an expression can be written in this form. Okay? And nu will be called a transverse measure, and it's actually a family of measures. The same measure can be represented using different arcs in a different way. On each arc, I actually get a measure which is actually uniquely determined by the measure on the surface. So that assignment, sorry? These are conditional measures on transverse arcs. That assignment is you can reconstruct a two-dimensional measure which is horizontal invariant in the horizontal direction from these conditional measures on arcs. 1 second. And so this now will be the conditional measure on the arc alpha.
This measure nu is invariant under anything?
Nu is invariant under the horizontal. Thank you. So this is a horizontally invariant. Horizontal straight line flow invariant. Okay? Is that your question? Okay, I'm only interested in measures which are horizontally invariant for the straight line flow in the horizontal direction. Okay, to summarize, what am I doing? Let's look at this formula. What am I doing? I'm doing exactly what the Horocycle flow does. I'm taking the original vector, not changing anything in the y coordinate, and in the x coordinate, I'm adding. Oops, I forgot my t. In the x coordinate, I'm adding a multiple of an integral, and this is the multiple of an integral with respect to some transverse measure. For the Horocycle flow, the transverse measure is the transverse measure which is related to Lebesgue measure. Here I want to add the transverse measure which is not related to Lebesgue measure, it's related to some other measure. What other measure? Well, usually there are no other measures, but on omega there are other measures, and I want to use those measures. Yeah.
Is the transformation you drew on that board
is what?
Is that picture an example about?
This picture is sort of supposed to explain to you what a transverse measure is. Oh, this is not a tremor, because this motion a priori has nothing to do with transverse measures. Okay, now let me give you examples of things which are actually tremors. Okay, so examples of
But
tremors.
somehow this VT depends on the choice of nu.
Right.
And the choice of nu, how can you make consistent choice along all of the elements
Very
of
good. That's
all
why it's measurable but not continuous. And in our setup, which is a simplified setup, the space of ergodic measures is either one-dimensional when it's uniquely ergodic, or it's two-dimensional when it's not uniquely ergodic. And in fact, when it's two-dimensional, there are two different ergodic measures, but they're swapped by a certain involution, and there's a symmetry. So in fact, there's just one thing that one might choose. That's a very simplified situation in our simple case. But in general, what you can always perform this, and then the input is not a real parameter t, but you need to specify the ergodic measure as part of your input. And another technicality is why I'm choosing a signed measure here with total mass 0. Let me just remind you what a signed measure is. A signed measure is something that looks like this, where nu plus and nu minus are both positive measure, and then the total mass is the difference of these. So I want this to be balanced in the sense that the total mass is 0, and this is the mass. And there's something called the total variation. I don't know if this is the standard terminology, in fact. But what I mean by total mass is I want the positive part and the negative part of the signed measures to be balanced with respect to each other. That's what this says. Okay, let's show you the pictures from yesterday that you liked, I hope. Hit it. Take it away. I don't know how people say this in shows. So you're supposed to see something appearing on the... Very good. Okay, so maybe I can make this larger. So this is that picture from yesterday, which was related to two ways of presenting one surface as made up of two tori. Okay, let's think about the easier case of the simple decomposition. So we have here simple decomposition, namely into two squares separated by this horizontal segment, and we have a more complicated picture where you have two cylinders which are in two different colors separated by this diagonal line. So first of all, let's talk about the two torus decomposition in which you have a splitting along the vertical direction. Well, you can put a horizontal invariant measure on this union by putting Lebesgue measure on the left-hand side and the zero measure on the right-hand side. Okay? That will also be horizontal invariant. Okay? And if I wanted to make it of total mass 0, I can put a signed measure, a positive signed Lebesgue measure on the left of mass 1 and negative mass minus 1 on the right-hand side. Okay? And now let's think about this formula for that particular measure. What's going to happen is that this the left-hand torus, will tilt according to Horocycle flow, positive Horocycle flow. The slit won't change because it's a horizontal segment, and this torus, this square, will become a parallelogram, and it will be tilted to the right. And on the other side, it'll be similar, but you'll tilt it to the left because this formula will just give us a negative time Horocycle flow on the left. And so you're tilting one of these tori in one direction, and you're tilting the other torus in the other direction using the Horocycle flow. Notice that you're moving away from the E locus. The E locus is the locus where you have two identical tori glued along a slit, and in some sense you're forcing these tori to be not identical in a very fast, very economical way. So this would be an example of a tremor. Okay? Now you can do the same thing with red line, okay, it's not horizontal, but just rotate your heads and imagine that the diagonal line, this long line, is now horizontal. Thank you very much for tilting your head. And so you can sort of do the same. And you can shear, you're going to have two long tori. And you can shear one of them in one direction, the other one in the other direction, and you're going to get a new surface. And that's going to be the image of the surface under a tremor. Now, these examples are not interesting in the sense that they don't talk about minimal non-uniquely ergodic directions. These are non-uniquely ergodic directions, but they're not minimal. They have splittings into two pieces. But as I told you yesterday, you can take limits of such pictures and get minimal non-uniquely ergodic surfaces. And that's exactly what is going on. We're taking minimal non-uniquely ergodic surfaces. They have approximations that look like this. On the approximations, we're tilting one cylinder in one direction, the other cylinder in the other direction, and we're taking limits. Okay? So that's what the tremor map does. Okay? So I've basically explained to you what a tremor map is, and I've explained to you that it centralizes the Horocycle flow, and the rest of the properties that I told you about are sort of the heart of the argument, is to prove that you have you stay bounded, but the distance goes to 0 on average. That's kind of a crucial thing. And in order to make sense of why the distance goes to 0 on average, the end of the day, the point is that you have to analyze pictures of this type, these checkerboard patterns, and you have to understand that the amount by which the tremored surface differs from the initial surface sort of has, so what you should imagine here is that you have these two pictures. This line is horizontal, and the diagonal line is also super close to being horizontal. Okay, so in other words, I'm trying to construct two approximations of a horizontally invariant measure on a horizontally minimal surface. So just imagine that this is almost horizontal, and this line is also almost horizontal. It's still a fact that you can have this imbalance. And when you see this imbalance, this tremor map will really move you away from the eigenform locus, from the E locus. But on the other hand, if you have a balanced picture and you just move these things, you just do these tremors on these red lines and the picture is balanced, everything will sort of cancel out and you won't move at all. So the point of why it is that the distance goes to 0 on average has to do with the fact that typically when you look at these pictures, the two colors are balanced. Okay, that's kind of like one of the main points, which I can't describe in any other way. Okay, so that was kind of a slightly too long explanation of how we get these erratic centralizers. And now let me say how one uses, are there any questions about this? Now I want to say how one uses that to deduce the other statements.
Interval of t for which zt is defined. Is it?
It's infinite. It's defined for all R, right. And in fact, as it's important, now the importance is coming now, in fact, as you increase t, and you look at all of omega and let t go to infinity, you become dense in H11. You can show that you go everywhere in H11. Yeah, let me write that down because it's crucial for the rest. So proposition. Union T and R x at omega ZTX is dense in H11. Let me use this proposition and another proposition. If x is in omega, then ux is generic for the SL2R invariant measure on E. I'm reminding you that omega was some set of codimension 1/2 on this set space E. And actually on the space E, we do have a complete classification of Horocycle invariant measures and orbit closures, and we have a genericity statement. So these points are actually generic for the Horocycle invariant measure. Okay, let's now start putting together the pieces, and let's see why we get non-generic points for the Horocycle flow. Construction of points for which and which are not generic for any measure. Okay, first step. Let's let M1 be the SL2R invariant measure on E. Okay, and let's let X1 be ZTX for X in omega. So I'm reminding you, if X is in omega, by this proposition, it's a generic point for M1. Let's call this 1, and this guy 2. So by proposition 2, X is generic. The U orbit of X is generic for M1. Therefore, so is UX1, right? Because the distance between X and X1 along the Horocycle flow is 0 on average. So whatever happens, whatever happens in Vegas stays in Vegas. On average, if X is well behaved and X1 is almost always close to X, then X1 is also well behaved, right? So this uses the fact that these two orbits are arbitrarily close to each other on average. So what have we found now? We have now have a dense set of points on in H11 which are generic for M1.
This is already something that doesn't happen in the
Yeah.
homogeneous setting.
Right. Homogeneous, I was just about to say that. In homogeneous setting, this doesn't happen. Exactly. Why not? What happens in the homogeneous setting? Homogeneous setting, you have a big measure. And with respect to this big measure, there are plenty of ergodic other measures. And the collection of other ergodic measures, the generic points for them are dense. But there is no one specific measure living on a smaller dimensional variety for which that particular measure has a dense collection of generic points, dense in the support of another measure. So now we're going to use that in step 2 and use a Baire category argument to conclude. So step 2, Baire category. Let's let M2 be the SL2R invariant measure on the entire space. This is a different measure, SL2R ergodic, and let's let F have a different integral Let's let F be a function that has a different integral for these two different measures. And let's take epsilon less than the difference between these two integrals, half the distance between these two integrals. And now let's define the following sets. So let's see. Let's say GT epsilon F. So given a real number T and these two things, epsilon and f, and I mean j is either 1 or 2, let's let this set be the set of all x's in H11, such that if you take the ergodic, the Birkhoff average of length t starting at this point, and you subtract the target integral, you end up having a result which is accurate up to this epsilon. So this is in a particular time, fixed time interval, fixed epsilon, all these numbers are fixed. This is an open set. It's an open set in the stratum. And therefore, we can talk about the following thing. So the, I guess T epsilon fj. This collection is now a dense G delta. So first of all, each of these, this is a countable intersection of open sets. And each of these open sets are dense because they contain the generic points for these measures. And I just told you that for M1 we have a dense collection of generic measures. And for M2 we definitely do by ergodicity. So this is a dense G delta of, and let's call this whole thing Yj. Okay? So this is a dense G delta set, of x's which satisfy this property 1 over Tn 0 to Tn Fus x ds minus ij that's an epsilon along a subsequence Tn going to infinity. Right? If you belong to this set, then infinitely often if you belong to this intersection, then infinitely often you belong to these sets. Okay, this is a dense G delta, the other guy is a dense D delta, and any point in the intersection will have fluctuations in its ergodic intervals. That's how one proves the first statement about existence of points which are not generic for any measure. Now, in order to prove, I'll say this very, very roughly, in order to prove the theorem about Hausdorff dimension, let me just say what it is we actually find. So we find x1 of the form ztx. X is a point in omega, such that the orbit closure of x under U, on the one hand, it's contained in all the union over x in x in omega, sorry, x1 in omega, sorry, x in E, x not horizontally uniquely ergodic. Let me write it out in full and then I'll explain. So our orbit closure is trapped between two sets which are very, very similar to each other. Sorry, this should be okay. Two sets which are very, very similar to each other. First of all, I'll remind you what the definition of omega is. The definition of omega is almost exactly the same as this. It's the set of surfaces in E which are horizontally not uniquely ergodic, and on top of that are minimal. Okay? So the only difference in some sense between this union being taken here and union being taken here is here I've added surfaces which have these splittings. In other words, surfaces which actually do look exactly like this and not approximated by things that looks like that. Oh, sorry. This is x1, this is x1. Thank you. A is here, x1, x1. Thank you.
View x1? No?
What was the question? Oh, I'm sorry. X1, this is a UX1, and this is an X. How about this? X, X, X. Okay? Thank you. So again, what's the difference between this union here and union here? Here we're taking all the guys which are non-uniquely ergodic and minimal, and we're taking their spike. And the length of the spike is this parameter A in a certain sense. Okay? And here we're taking the same things, except we're only adding a slightly larger set. We're adding the ones which are also horizontally non-minimal, which means we're adding surfaces which have some splittings in the horizontal directions. It's a small collection, but it's enough to force the closure to be trapped inside it. So it makes this closure stay in this set. It doesn't. These two sets actually have the same dimension. It's easy to show, and that's the structure. And to get this containment, okay, this containment will always be. This is a closed set, it turns out. So this containment will always be true for surfaces of this type. The main point is to be able to take one Horocycle orbit which captures all of these spikes. Okay? How do you do that? Well, there's the guy called John Chaika on our team, and Chaika is a student, a fan of Baer, and he likes to use the Baer category argument over and over and over again. And so there's a kind of a Baer category argument saying that if you can find one point which starts somewhere and ends up somewhere else, then there's an open set of points that start that place and end up somewhere else. And you could start playing games, kind of Baer category games with these sets. And so you play like a Baer category argument inside this space. And the main point of the Baer category argument at the end of the day is exactly, again, analyzing these pictures and sort of forcing points to move up and along these spikes that I tried to tell you about. I hope this was satisfying and you got an idea of what's going on. So thank you for your attention.
So thank Barak for this mini course on spiky fish. Questions?
Yeah.
Could you say what you mean by UX is generic for the SL2R measure?
Yeah, you have two measures in the game. So this was a diagram that we had before. This is H11, and here inside there's this set E. Okay, this is a 9-dimensional space, and this is a 5-dimensional space. And there are two measures in the picture. There's kind of a globally supported measure on all of H11, which is given by the period coordinates on H. It's the Maser-Veach measure on H11. And there's another measure, SL2R invariant measure, which is given by McMullen's classification of invariant measures on E. Okay, so this I called the one on E M1, and the globally supported measure I called M2. Now it turns out, by our arguments, that the collection of points which are generic for M1 is dense, not only in E, but in all of H11. So everywhere here, there's a dense collection of points which are generic for a measure which they don't belong to its support. But basically, what these orbits are doing is they're kind of tracking another point inside this thing which is generic for it. So on average, they come very, very close, and they're generic for this measure. At the same time, there's obviously a dense set of points here which is generic for M2 in the same space. Then you can run Baer category. Okay?
No.
No.
So, I mean, so you suppose so you mean that for all points in UX, I mean, all the points in UX are in.
Not all the points in.
Okay.
What's UX?
I
You,
don't know. The proposition 2 says UX is there with respect to M1.
yeah, so X in that proposition was of this form. Maybe my notation is changed, is different, but this is for surfaces which have this particular form. Notice that they don't belong to E, okay? But nevertheless, they are generic for the measure on E. Okay?
And when you say UX is generic, you mean almost every point, or you mean?
No, this is one orbit. UX is an
so
orbit.
The orbit is
You do the
under the SO2 action.
no under the Horocycle action. Sorry, should have said that. UX generic for mu just means this.
Okay.
Thanks for. Too bad you didn't ask that earlier, but yeah.
Can you define, do you have a well-defined map from the M1 generic measure, generic points to E, to omega?
From all M1 generic points to omega?
I mean, attached to each one.
We have no, there's a map from the ones that we construct. The ones that we construct are exactly of X is exactly of this form, and in fact this is an injective. This is an injective map. So in other words, if X is of this form, then there's a unique A and there's a unique X0 such that you get this. So for these constructed maps, you can sort of push them back down. I don't know about other generic points. Probably they don't exist, but I don't have a proof.
I need to stop. We have a short break, so we probably need to stop now the questions, and people should ask questions to Barak in private. But we thank Barak again for this.